This first chapter is going to be about preliminaries. I don't intend to go fast at all. I rather have this first session to be as light as possible. We will have time to complicate our life later. So this first chapter is the first part is going to be on basic definitions of the algebras, which I assume that you're familiar with. The second part is going to be on complex and simple basics of the root space composition. And the last will be about representations. On the representations of complex semi-simple algebras. Okay? So I'm assuming that everyone here knows what a Lie algebra is, what a Lie algebra homomorphism is, and by extension, what an isomorphism is, morphism and what. So just three considerations. While we could do general theory on the algebra by assuming certain conditions of being algebraically closed or characteristic, we're going to just think that our base fields are going to be either the real numbers or the complex numbers. All the Lie algebras are going to be assumed to be finite dimensional. We will denote them by Gothic letters, and their elements will be denoted by capital letters. For example, an element of G would be, for example, a capital X. And the Lie bracket is going to be denoted as usual. Okay? So, first, suppose we have the algebra G over the field K. Okay? If there's any problem with the handwriting that you can, or you have a question, then feel free to ask. Alberto Martin says. Algebra. Okay, let G be a Lie algebra. Since the bracket is bilinear, we can think of it as the bracket as a map from G to the set of homomorphisms from G to G. That is, we have a map which we denote by R, which goes from the Lie algebra G to the vector space L of G. So this is the vector space of all endomorphisms of G, with the Lie algebra structure induced by the commutator xy minus yx. So this is going to take an element of x into x, which goes from G to G, takes y to the Lie bracket xy. So it's known that this is a Lie algebra homomorphism, and it's called the adjoint representation of the Lie algebra. So this is the adjoint representation. Okay. So, more on these algebras of endomorphisms. So, apart from this Lie algebra, we also have a subspace, which will be also a subalgebra of all the derivations of G. So we have this derivative G of all linear maps from G to G, such that D is a derivation. So these are the K-linear maps which satisfy the Leibniz rule. So D applied to a bracket xy is dx times y plus x times dy. So it's known that this is a Lie subalgebra of GL. More than that, it's easy to check by the Jacobi identity that every transformation at x is a derivation of G. So this contains at G. Okay? So this is a Lie subalgebra of G of G. This is a Lie subalgebra of the derivation, so it's a Lie subalgebra of here. But more than that, this is an ideal. Okay? And it's an ideal because one can check very easily that if you take a derivation and a transformation of the form x, this is equal to at dx. Okay?
So it's an ideal in the derivation, right?
Yes, it's an ideal here. It need not be an ideal in the set of all endomorphisms. Okay. Okay, so for now, I've just talked about some examples of the algebras, and now I'm going to talk about some Lie groups associated to G. So we have the general linear group of G, which is the group of all automorphisms, linear automorphisms of G. So this is a Lie group, and in this group is contained a subgroup, which we denote by AUT of G, of all Lie algebra automorphisms. Okay, so this is here. We also define the group of inner automorphisms, which we denote by 8G, and this we define by means of connected Lie groups. So this is going to be the connected subgroup of the group of automorphisms whose Lie algebra is at G. Okay, so this is not to exist because use of algebras are related to connected subgroups. And well, what do we know? Well, from here we know that the group of inner automorphisms is contained in all the automorphisms, which are contained in all the linear automorphisms. But more than that, since G is an ideal of the set of derivations, it follows that the group of inner morphisms is a normal subgroup of the group of automorphisms, although it's not necessarily a normal subgroup of here. So in G is normal here. Also, as a consequence of the fact that this is the connected subgroup with the algebra at G, one can describe the group of inner automorphisms as the group generated by all transformations of the form e to the x such x. This is because when you take Lie subalgebra, the connected subgroup whose Lie subalgebra is, let's call it h, is the group generated by all exponentials of h, where h is another being. Okay. So, as I said before, this is a Lie subgroup, and its Lie algebra is known to be the algebra of derivations of G. So, the Lie algebra is algebra of form. Okay. Can you read this from home? Can you hear me well?
It's reasonable, I would say. I mean, you need to guess a little bit, but like if you watch it while you're actually saying it, I think it's fine. So you can altogether you can understand it. Oh yeah, that's actually a little bit better.
Yeah, the problem is that we will have to change.
But the problem is with the audio.
No, but like you can zoom in just a little bit, like so that the entirety of the board is seen, but like it's still a little bit better than it was like in the beginning.
All right.
Yeah. I think this is reasonable. Yeah, I think it's fine.
Okay. Okay. Perfect.
Thanks.
So I talked about the adjoint representation of an algebra, and I'm going to talk about the adjoint representation of a Lie group. Also, just one small comment on the group of inner automorphisms. As I said before, G could be a complex Lie algebra. When G is complex, we take the realification of G, and we take the group of inner automorphisms or the realification. Okay, they are the same. Okay, so the adjoint representation. Now, suppose that G is a Lie group with the algebra.
Sorry, can you explain that last bit again?
Okay. Let's see.
I mean, the part where you
where I
G
said
complex.
G complex. Okay. So suppose G is a complex algebra. Okay. G complex. Okay. When G is complex, we can take the realification of G, which is simply forgetting about scalar multiplication with complex numbers, and what we get is a real algebra whose dimension is twice the complex dimension of G. So when we are talking about the group of inner automorphisms of G, when G is complex, we define it as the group of inner automorphisms of its realification. So why does this make sense? Because this is generated by all the exponentials of all at x. Okay? But even if G is real or complex, at x is the same. So we really don't need to think about the complex structure. So in order to talk about the groups, which will be assumed to be real, there is no problem in finding this. Okay. More details can be found, for example, in Knapp's book, which makes a better clarification than what I just said. Okay. Because think that the composition of matrices or endomorphisms is independent of the linear structure. Composing does not use the scalar multiplication. Okay, so we have a Lie group with the algebra G. So given an element of the group, one can associate an automorphism of G, which we call alpha sub G, by letting x go to dx minus 1. So it's very easy to check that this is a homomorphism, and that alpha G equals to alpha H equals to alpha GH. So this is a homomorphism from the Lie group G to the group of automorphisms of G. So since alpha G is an automorphism of the Lie group, if we take the derivative, which let's define it by G alpha G in the identity element, this would go to the tangent space of G to itself, but we already know that this is equal to the Lie algebra of G. And this is a Lie algebra homomorphism whose inverse is the derivative of alpha G minus 1. So this is, again, an automorphism, but of Lie algebras. Okay? So we will give this a name. We will call it X, but with a capital A. Let G, sorry. Let G equals the differential of this conjugation map at the identity element. So this is an automorphism. And we can also think now of the map Al, which takes G to a G. So we have a map Al, which takes an element from G to a G, which is in the group of all linear isomorphisms of G. GL, G. Okay? So this is, it's easy to check that this is a Lie group homomorphism because taking G to alpha G is a group homomorphism. And it's called the adjoint representation of Lie group G. So a very important fact here is that this adjoint representation and the adjoint representation of the algebras are related in the following way. The differential of the capital A adjoint representation of identity is equal to the adjoint representation of the algebra. Okay? So more definitions regarding this representation. The same that and G is the adjoint linear group of G. Okay? And also recall that when we took the image of this adjoint representation, it was an idea in the list of algebra. So because of this fact, we can also say that this group will be a Lie normal subgroup of the group of linear homomorphisms. Okay? So at G is a normal subgroup of the group of automorphisms. And now here comes an interesting fact, and it's that recall that the group of linear automorphisms of a Lie algebra does not make any explicit assumption that the Lie algebra comes from a certain Lie group. But what this is saying is that we can realize the group of linear automorphisms as the image of the adjoint representation of a Lie group when this is connected. So formally, we have the following fact, which is that if G is connected, then the G is equal to the homomorphisms, and also the kernel of the adjoint representation is equal to the center of Z. So from this, it's usually said that the group of linear automorphisms of the Lie algebra is like a universal version of this at G when G is a Lie group. So it's really easy to prove this. It's just checking that this and this have the same Lie algebra, which is at G when G is the Lie algebra. And for this equality, when G is connected, a homomorphism is trivial if and only its differential is trivial. Okay, so an element would be the kernel of A, since A is the differential of taking G to alpha G, then the add of G is 0 if and only if this map is 0. Or trivial, I should say. But if this map is trivial, this is the same as saying that G commutes with every element. So this is what it follows. So now the next thing we're going to do is to introduce the killing form, taking some of its properties. So first, a general definition. Let B be a bilinear form on G. Okay. So we will say that B is invariant if and only if we have the following equation. So what does this mean? So if you think about it, this is just like saying in a certain way that the elements of G are anti-symmetric. Okay? So if this were a scalar product, it would be just like saying that they are not self-adjoint, but they are anti-self-adjoint, skew-symmetric. And it is to see, once again, by making an analogy with saying that the algebra of orthogonal matrices is the algebra of skew-symmetric matrices, it can be shown that this is equivalent to saying that B of alpha x alpha 1 is equal to B x 1 for every x, y, and z, and alpha and inner automorphism. Okay, keep in mind the idea of this being that the elements of G are skew-symmetric if and only if their exponentials are orthogonal transformations. So it's an analogy because in principle, the bilinear form need not be non-degenerate or scalar product or anything like that, but it's a way to remember this. So there is a canonical bilinear form that we can define on every Lie algebra, which is called the killing form. And we will denote it by capital B, G and G. Okay. Onishchik prefers the notation kappa sub G, but B is also a standard notation. So I'll take the liberty to use this. And it will be defined by B x comma y to be the trace of x times at y. Okay. So since we're taking a trace, we are assuming that it is dimensional, which is not a problem for us. And also, while the product of matrices is not commutative, it's true that after taking the trace, one can change these two factors, the order of these two factors. So it follows that B is symmetric. And invariant. This would need a small proof, but it's just algebraic computations.
One comment. But this killing form is not just invariant by inner automorphism.
Yeah, that was what I was going to say.
Okay. No, because it's strange that we define, well, maybe it's Onishchik's fault, but he defines the invariant to be invariant under inner automorphisms.
Yes.
To be invariant under all automorphisms.
Yes. So what B satisfies is stronger than this. So this the fact that it's invariant under all automorphisms implies this.
Yeah,
But
for sure.
unless the group of automorphisms were connected, these two things wouldn't be equivalent necessarily.
Yeah.
And again,
So we will follow this definition that some bilinear form is invariant if it's invariant under inner automorphisms.
under inner automorphisms, yes.
Okay.
Again, we're thinking of identity components or connected groups. So, like Alberto just said, we have that B of theta x, theta y is equal to B x y when x and y are elements of G, and theta is an automorphism of G. Okay? So, what's really useful about this Killing form is that it characterizes some algebraic properties of the algebras that, in principle, would be hard to identify. For example, we will see that this characterizes when the algebra is semi-simple or when it is solvable. Which, for example, checking that the algebra is solvable is more or less doable, but checking that it's semi-simple would take more effort. Okay. Oh, and another property that should be noted is that when you take a list of algebra of G, the Killing form of this algebra, one might think that it should be the restriction of the Killing form of the total space to the list of algebra. That's not necessarily true. There are examples in the main. There is an example in the non-abelian dimension to the algebra. But what is true is that if H is an idea of G, then the Killing form of H is equal to the Killing form of G restricted to H. Again, this is not true in general. And one example is not true for subalgebras. For subalgebras, yes. For subalgebras. And one example can be seen in G being the algebra of affine transformations of the real line, which is defined by, I can put R, but I can put really any arbitrary field. So a Lie algebra generated by two elements, satisfying the relationship x, y equals 1. So in this case, one can see that the Killing form restricted to the span of x is non-zero, but if you but the Killing form of the span of x should be 0 because a one-dimensional Lie algebra is necessarily abelian. Okay, so I think it was the span of x, but if it was not the span of x, it should be the span of x. One of those two. One will have to go through the computation of the Killing form, but in this case, it's low-dimensional, so it's at the very least doable. Okay, so about this characterization of algebraic properties, we're going to recall what a simple Lie algebra is, what a semi-simple Lie algebra is. So, first, we all know what a solvable Lie algebra is, no? Solvable and nilpotent Lie algebras. Okay.
Sorry, before you said that this was the subalgebra where this doesn't hold, the subalgebra is spanned by x, right?
I think it was the subalgebra spanned by x.
Well, because the other one is an ideal, right?
Yes.
Okay.
Yes,
Okay.
So, I don't remember the metrics for the Killing form, but what I do remember is that there is a diagonal element which is non-zero, and that's where the contradiction is.
Okay.
I mean, we can go through the computation. It's not too hard, but
Yeah, you want. Yeah.
Okay, so well, quick review of what the algebra was when it was semi-simple. Okay, so G is simple if its dimension is greater than 1, and G contains no abelian, no ideas. The order of the more than 0 and G is semi-simple if it is not abelian and it contains and it's only solvable idea is 0. So I said solvable, but because since solvable algebras contain an abelian ideal, there is no problem in changing the solvable by abelian. So it's just a small detail. And so semi-simplicity can be characterized in terms of the killing form as well as solvability. So we have the following criteria. The first is the Cartan criterion for solvability. And it is that G is solvable if and only if G and its commutator are pairwise orthogonal with respect to the killing form.
Maybe you should remember what is solvable.
Okay, so
Unimportant.
yes, no problem. No problem. Didn't get away with not putting it. Okay, so the algebra. G. Well, first, the commutator of two ideals is the linear span of all possible brackets of elements in the ideals. Okay, so we take a Lie algebra D, and we can define two commutator series. So the first is the no, I'm not sure. Center, yeah, that's one. The one associated to nilpotency. The other one, how was it called?
Low,
I just lower ascending series. Let's just check here. We're not using anything bad.
someone at home? No?
Yeah, does anyone remember the name? The commutator series? The commutator series.
They're right. Yeah.
Aren't they called like upper and lower central series or something?
Yeah, but the lower central series is the one associated to nilpotency, no? So when you take the GI times G instead of GI times GI. So the other one here in Knapp's book is called the commutator series. Maybe it's also called the derived series. But
Yeah, here they call the derived series.
okay,
Because
so
you take the commutator of commutator.
yes. So we take let's first talk about the derived series. the right commutator is. So it's defined in the following way. So we take G0 equals to be the whole Lie algebra. Okay? And we take Gi plus 1 to be a bracket of Gi with itself. So it's easy to check that each Gi is an ideal of every member of the series that goes before. And we have a chain of the form G equals 0. It contains 1, contains 2. And since we are in finite dimension, notice that if, for example, G1 is smaller than G0, strictly smaller, then it must be because its dimension is strictly smaller. So what will happen is that this will be strictly decreasing until it reaches a point in which Gi is equal to Gi plus 1. This has to happen because G is assumed to be finite dimensional. And the moment that Gi is equal to Gi plus 1, all the G super J's that go after it will have to be equal to Gi. Okay? So this always stops, but it will not stop at 0. Okay? You say that G is solvable if G equals 0 for some k. Okay, and when we're thinking of the minimum k for which gk is 0, we say that G is solvable in k steps. And it's easy to see that if gk is 0, then gk minus 1 is a billion, right? So sum of all algebras contain a non-trivial abelian idea, unless the algebra which we started with was 0. Okay. I think I put myself here. And apart from the commutator series, we have the lower central series. Which is defined in the following way. So now we start by G sub 0, which will be G, and Gi plus 1 will be the commutator of G with Gi. Okay, so again, everything is an ideal of what comes before it, and we have a chain G equals to 0, contains 1, contains 2, and eventually this will stop because of finite dimension, and we will say that G is nilpotent if Gi is equal to 0 for some. So say that G is nilpotent if Gk equals 0. So now, as I said before, some of our algebras have an abelian idea. So if we have a non-zero nilpotent Lie algebra, and Gk is the least k for which, and k is the least for which Gk is 0, then this means that the bracket of G times Gk minus 1 must be 0. But this is non-zero. So what this means is that there is a non-trivial subspace which commutes with all G. This is the same as saying that the center, which is the space of all elements which commute with G, is non-zero. So solvables of algebras have a non-zero abelian ideals, and nilpotent algebra and nilpotent algebras have non-zero center. And since GK is contained, no, I always mess this one up. Since, yeah, this is the correct one. The G sub k is always bigger than GK here. So what this means is that if this is zero, this needs to be zero. So nilpotent algebras are always solvable. Okay. Just want an example. The clearest one is to think about triangular matrices. The algebra for triangular matrices is upper triangular matrix, for example, solvable, but to say it correctly, yes, the Lie algebra is solvable, and the Lie algebra of all upper triangular matrices which have zeros on the diagonal is nilpotent. Okay. And there are also the theorems of Lie and Engel that, in some sense, say that we can always think of those algebras when we are working with representations of Lie algebras, which are solvable or nilpotent. So we were at Cartan's criteria. So as I said before, I'll just put this over the criteria again. So so the criterion for solvability says that G is solvable if and only if G and its first commutation are orthogonal with respect to the Killing formula. Okay? And semi-simplicity the criterion for semi-simplicity says that G is semi-simple if and only if B is non-degenerate. For the sake of completeness, let's first recall what it means for a bilinear form to be degenerate, non-degenerate. So this is the same as saying that if we take an element of G such that the Killing form evaluated at xy is equal to 0 or y, then it must be that x is equal to 0. Okay? So what this allows us to do is to give an identification of G with its dual space. More on that later. And feel free to ask. So from the criterion of semi-simplicity, one can check that semi-simple algebras are precisely subs of simple algebras. G. G is semi-simple if and only if G can be split as a direct sum of ideals which are simple and this decomposition is unique. In fact, what we have is that ideals of G are precisely all possible sums of subsets of these G sub I's. So for example, G1 is an ideal, G1 plus G4 is an ideal, and so on. And the ideal must be of that form. Oh, and a very important consequence of this is that by taking this expression, one checks that for semi-simple algebras, the first commutator is equal to the whole G. Okay? So how are you holding up?
How do you go?
How are you holding up? Well, now it's more or less simple, no?
Yeah.
Okay, so more facts on semi-simple algebra. So I said before that all elements of the form X are derivations, but it's not true that all derivations are of the form X. Well, this is true when G is semi-simple. So fact. If G is semi-simple, then the Lie algebra at G is equal to the Lie algebra of derivations of G. And what this means, when we pass this information on to connected the groups, is that the group of inner automorphisms is maybe not the group of all automorphisms, but it's the identity component. So this this superscript 0 means taking the connected component, which contains the identity, which is known to be a normal subgroup, and it's open and it's closed, and everything good. Okay. Yes. More. So we know about semi-simple, important, Boolean algebras, and more definitions about this. We have that the Lie algebra G is reflective if it satisfies the following property. If for every idea A G, there is another idea B G such that G is the direct sum of A and B. Okay? So this property is that in an idea we can split G as the sum of X and another idea which can be chosen for B. So from this decomposition we can give a longer decomposition of G into ideals which would be either abelian and one-dimensional or simple. So ideals which have no smaller ideals. One can check that the sum of all abelian one-dimensional algebras will be the center of G, and the sum of all simple Lie algebras would be the commutator of G itself. So this is equivalent to saying that G is equal to the commutators of G with itself plus the center of G. So I'm just going to recall what the center of G is. Set of all elements such that they commute all other elements of it. And it's also easily seen as the kernel of the lowercase r representation. So this is an abelian ideal. And since this can be written as the sum of simple ideals, it follows that this commutator is semisimple. So we have that it has an abelian part and a semisimple part. So the definition is equivalent to this, and it's also equivalent to G being the sum of something abelian and something semisimple. Okay. Just a small example, there is an easy way to construct examples of productive algebras when we talk about algebras of matrices. So this is the simplest example we can find. Example. If G is a real algebra of matrices, I think Onishchik is more of a fan of using N as a subscript. If G is a algebra of GL and K, where K are the real or the complex numbers, we can also take the quaternions, but we're going to restrict ourselves to real or complex. So if this subalgebra satisfies that given any element of G, its conjugate transpose is in G, then G is reductive. Okay? And why this is true? Because one can take any ideal, and if you take the orthogonal complement with respect to the usual linear product, it's also an ideal which satisfies the sum property. Okay? So this is an easy way to generate out of examples. The simplest example.
Sorry, can you say
yes. You take any ideal of G. Okay? So you take the orthogonal complement with respect to the standard usual product, which is trace x y transpose. So plus 1 plus 1 y sub I conjugate. So you can check that the orthogonal complement with respect to this scalar product is again an ideal, and because it's an orthogonal complement, you have this property. Okay. I can give you a reference if you like. Do you want it now? Yes. I can give you a reference means it's in the handbook. Okay. So, very trivial example. The GLN C. So this must split as its commutator and its center. Does anybody want to try to tell me which are those parts? So which is the commutator of GL and C? S and C. So what's the other part? A very important clue. The dimension of S and C is the dimension of GL and C minus 1. So tell me an element which commutes with all matrices. The identity. This is the center, and this is the semisimple part, which is also the commutator. Okay. So now comes the part about hard measure. So no, you can see. We can submit it to popular votes. Does anyone want to remember what invariant integration is all about?
Well, okay.
There are more people than me. Is anybody scared of invariant integration? I'm hearing nothing.
Right, okay, saying that it exists.
I mean, I'm not
And
going
it
to
provides an invariant event product.
Okay, so
I don't know about.
I'm just going to
guys
say
don't-
I'm just going to say two things about invariant integration. Okay, just two things.
Okay, so
Invariant integration. First, it exists. Okay, so when you have a compact Lie group, one can define a functional which takes continuous functions to the integral of this integral, and this is a linear functional, it's positive, it induces a measure in G, and it can be normalized so that G has volume 1. And this integration is, for example, like integration in Rn, in the sense that changing variables by multiplying by an element or inverting does not change the value of the integral. Okay? And this is very easy to build in a Lie group, but it can also be built in compact topological groups. And the most notable application of invariant integration.
Linear means right?
What?
Translate right?
Can you repeat?
By multiplying, you mean that it's adding, right?
Yes.
When
I
you
can
look
put-
at the Rn integral.
Yes, it would be the integral of f of x plus y
Yeah.
dx is equal to the integral of x dx.
Yeah.
So here it would be f of gh or hg is equal to the integral of f of g.
Okay.
Okay, and the most important application is for representations of compact groups. Okay, so for representations of compact groups, one can construct with invariant integration a fixed vector, which may be zero, so it's not, so it doesn't really guarantee the existence of an invariant subspace. But we can also build a fixed scalar product, which is more important. This is known as the theorem of Weil. Theorem of Weil. Take Lie group homomorphism rho from G to GL B. Okay, so this is called a representation. B can be real or complex. So depending on if B is real or complex, we take a scalar product. Scalar product. If B is real, we take a positive definite bilinear form, and when B is complex, we take a positive definite Hermitian form. So define a new scalar product by saying that the product of B on B is the integral of G on G of G U of G B C. Okay? So this scalar product is well defined, and every element of G is now taken into an isometry of this vector space via this scalar product. Okay, well,
Rho.
what?
Rho is a representation.
Rho is a representation, a group homomorphism. Yes, a rho of G is an isometry of the vector space we indulge with this linear scalar product. For example, this means that every compact subgroup of matrices must be contained in SPN ON or UN. We're talking about complex matrices. And I think that's enough about invariant integration. Okay. So
We don't believe in integration.
you don't believe in integration? Well, compact is like finite, integrating is like summing. I mean, it's not that. But do you believe in differential forms?
Yeah, that's
So what's the problem with integrating differential forms?
another issue.
Well, you can take this as an axiom. So there exists a scalar product which makes everything an isometry. So this is a new axiom of mathematics.
Okay.
Okay. So since we have about 15 minutes, so I'm going to try to finish this section on the basics, and for the next lecture we'll talk about the structure of complex semisimple algebras. So compact Lie algebras. So suppose we have a real Lie algebra. Now G must be a Lie algebra over the real numbers. G is a real Lie algebra. So we will say that G is compact if one can find an invariant scalar product from G. An invariant scalar product from G. Scalar product. So do you remember what an invariant form was?
Yeah.
It was a bilinear form in which the elements of a G acted as anti-symmetric transformations. So facts. First, the Lie algebra of a compact group compact group is compact. And this is a direct consequence of this axiom applied to the adjoint representation. Okay. Another fact is that compact Lie algebras are reductive. The proof is exactly the same as with matrices invariant under conjugation and transposition, and invariance under conjugation and transposition. You just take the invariant scalar product, and the orthogonal of any ideal is again an ideal. Okay. So in particular, compact Lie algebras are broken up as their center plus their commutator, where the commutator is always semi-simple.
The converse of the first fact isn't true.
The converse of the first fact isn't true.
What is the converse?
That if
You have a
you have a compact Lie algebra, then there is a Lie group,
it's not
which is
compact.
compact.
That's still true.
Yes, it's the
What is not true is that every Lie group has a compact Lie. Sorry. What is not true is that, for instance, if you consider R as a Lie group, it's not compact. It's not a compact Lie group because topologically it's not compact, and it's the algebra is compact, so it's
compact. That's because it's also the Lie algebra of the circle.
But this is the algebra of the one-dimensional circle. Yeah.
You can also say that G is compact if the group of inner automorphisms is compact, and you can prove that this condition is equivalent to G being the algebra of compact Lie group.
Yeah.
But this is like a fully algebraic definition of compactness.
Yeah. I have one question here. So you give this definition of compact the algebra and say that it's compact if there is an invariant scalar product of G.
Yes.
And what about the outer automorphisms?
About the outer
Yeah, because maybe you have outer automorphisms that
do not act as isometries.
do not act as isometries. Could that happen?
I guess so. I think it's possible. I don't know off the top of my head if that's true. But probably yes, because, for example, if you take a non-connected Lie group, I think you can make some kind of semi-direct product or direct product by adding elements that do not act as isometries.
Is that a compact? Has that has a compact Lie algebra? Probably not.
For example, if you take, I mean, this is not really an answer to
Pick
your
an
question.
example of a compact Lie algebra.
Of a compact Lie algebra. No. So when, for example.
So yeah, you think that there are outer automorphisms that are not skew adjacent for the negative of the killing form of this?
I couldn't say at the top of my head. So what I try to do, if I wanted to make outer automorphisms or something like that, is to take SON,
Yeah.
and maybe make a semi-direct product with something finite. Maybe try to add from this group automorphisms which don't act as orthogonal transformations. But again, you're taking me off guard.
Yeah.
I'm sorry, did I get the question correctly that like if you take a compact Lie algebra, can it happen that the full automorphism group does not act by isometries on it if we take an invariant bilinear form?
Yes, that's the question.
Yeah, I get it. I mean, this can happen if and only if the full automorphism group, when we think of it as the subgroup of GL Gothic G, is not pre-compact, right? Because SOG is like the maximal compact subgroup of GLG. And this can only happen if it has infinitely many components, I think.
How many? You said?
Infinitely many.
But this is not going to happen for compact. For compact Lie algebras.
Maybe the adjoint.
Is it true that any compact Lie algebra has a finite outer automorphism group?
Yes, definitely. This is known by classification.
Oh, okay.
Yeah. So perhaps you have a proof for what I asked.
Yeah. Because then the full automorphism group is compact, because its identity component is compact and it has finitely many components. And then compact subgroups, if you have a compact subgroup of GLG, then you take a maximal compact subgroup containing it. And maximal compact subgroup of GLG are precisely SO for some inner product.
Okay, yeah, that's so nice. Could you write it up? So
yeah, I'll write it in chat.
Okay, perfect. Because now I cannot understand it perfectly.
Yeah, I'll write it in the chat in a minute.
Okay. Where were we? Oh, yeah. So one can check in this vector theorem that since every x is skew-symmetric, all its eigenvalues must be pure imaginary, and from this one can check that if G is compact, then the killing form is negative semi-definite. Okay? And more than that, B is negative even only if G is compact. And semi-simple. Okay. a last fact, which is related to what Jose asked before, is that if G is compact and semisimple, then the group of automorphisms and the group of inner automorphisms, so we're adding the hypothesis of semisimplicity, which is more than what you asked before. These are compact. Also, if G is compact, then G is the Lie algebra of a compact Lie group. Or a compact. Not all the Lie groups whose Lie algebra is compact are compact. For example, you can take a compact group and take the product with C, with Z, and that is never compact. Also, G is compact semisimple. And G taken as here is connected. Then G is compact. Okay. So that's all I wanted to talk about on compact algebras. And we're just going to see this last part on involutive automorphisms. It's very short. In maybe in 5 to 7 minutes, it should be over. So if you're familiar with, for example, the Cartan decomposition of a symmetric space, this will be very similar. Or even with simpler examples from linear algebra. So, okay, so suppose that G is a Lie algebra. Finite dimensions, and we have an involutive automorphism of G. So what does this mean? So we have an automorphism of G such that its square is the identity. Okay. So this theta is its own inverse. So it's easy to see that such a map is always diagonal. With minimal polynomial x squared minus 1 or x plus 1 or x minus 1, if it were a multiple of the identity. So its eigenvalues are plus or minus 1. So we have because of this being diagonalizable, we have that G must be the sum of two subspaces, which are in reality the eigenspaces for theta. So P plus is the eigenspace for 1. So the set of elements where theta acts as the identity, and G minus is equal to the eigenspace for minus 1. The set of all elements where theta acts as multiplying by minus 1. Not only that, but we have explicit formulas for the projections. We have the projections, which are 1 plus theta over 2. This is the projection over G plus. And 1 minus theta over 2 is the projection over G minus. And also, we have the following property relating G plus and G minus with brackets, which are first, G plus with itself is in G plus, which is equivalent to saying that G plus is a subalgebra. G plus with G minus is contained in G minus, and G minus and G minus is contained in G plus. Okay? And this information is enough to reconstruct an involutive automorphism. Convert. Given a direct sum decomposition G equals K plus P, satisfying these two relations,
No, es un número.
ah, siempre es un número.
No, pero sí, Iván. Es un mensaje de Iván para
Okay. So if we have this decomposition satisfying the three relations that the plus and the minus satisfy, then we can find an involutive automorphism, which acts as the identity on K and acts as the identity on P. So just the one given by taking the decomposition of an element in G as a part in K and a part in P, and making it act accordingly. So this is a linear isomorphism, but in reality, it is an automorphism with inverse itself. And G plus will be equal to K, and G minus will be equal. So what I'm saying is that an involution of the algebras determines these two subspaces satisfying these three bracket relations. And conversely, if we have two subspaces which are in direct sum that satisfy the three relations, they are precisely the eigenspaces for an involution of a set of the Lie algebra. So this can be thought in symmetric spaces, for example, as fractal involutions being the same as fractal decompositions. And so this is all that I wanted to talk for today. So it's nice that I finish here because next time we can directly start with the structure of complex semi-simple algebras without having to come back to this. Okay.